Okay, so now what is heap? A heap is a complete binary tree in which the value of each node is greater than or equal to the values of its children, if there is any. Technically, this is called a max heap. In a mean heap, the value of each node is less than or equal to the values of its children. So a max heap can be easily modified to make a mean heap. So in our discussion, the word heap will refer to a max heap. So now we'll see an example here. So we have a root which is 46, then it has two children, 39 and 28, and then so on the left side, if you look at the left side, 16 and 32 is the children of 39, and 14 and 3 yeah, okay, so 16 has two children, 14 and 3, and 32 has one child. So only the data member is shown that we want to prioritize here. Now here if you look at the total tree, it is a complete binary tree. So as we saw the definition of a complete binary tree, it could be a full binary tree, or it could be full by starting from left to right. So if you look at the left side is filled, and then the rest. So here, where is the greatest value in a heap always found? This one, the root. Okay, now dequeue. So dequeuing the object with the greatest value appears to be a theta 1 operation. However, after removing the object, we must turn the resultant structure into a heap again for the next dequeue. Fortunately, it only takes big O log n time to turn the structure back into a heap again, which is why dequeue in a heap is a big O log n operation. Okay, here is an example of dequeue. This is a complete binary tree. Now we'll save the root object in rem element. So we are assuming that rem element is equal to 46. Now copy object in last node into root object, which is this one. 5 is the last node into the root object. So we'll copy this object. So we are copying 5 into root object. So now the root is 5. Now we will remove the last node, which is 5. So we remove the last node, so 5 is gone. And then if the value of the greatest child of 5 is greater than 5, then swap with the greatest child. Now we'll swap here. You'll see the greatest child is 39. So 39 will be swapped with 5. So if you look at here, 39 is greater than 5, so we'll swap. So the theory is here that if the root child is smaller than the children, then it will swap. So like either way, you can say either way, if the children is if the greatest child greatest child means 5 has two children, 39 and 28. So from between 39 and 28, the greatest child is 39. So we'll compare with the 39 first. So when the greatest child is greater than 5, then it will swap with the root. So it is greater than 5, so it will swap like that. Okay, now the root is 39, and then one child is 5 and one child is 28. Now if you notice that 39 is correctly placed, it is guaranteed to be greater than or equal to its two children. So now if you look at here, it is 39 is greater than 5 and 28. Now it was the greatest child, so it is greater than the other child, 28. And it is greater than the element it was swapped with 5, or else we wouldn't have swapped. Now at this point we repeat the process using 5 as the parent. Now if you look at here, when 5 is the parent and 16 and 32 are the children, so if the value of the greatest child of 5 is greater than 5, then swap with the greatest child. Now between 16 and 32, the greatest child is 32 here. So we'll swap, we'll compare the 32 with 5 if it's greater than or not here. So 32 is greater than 5, so it will swap. Okay, so here you go. Now 32 is surely greater than 5 and 16, both of its children. Now if the value of the greatest child of 5 is greater than 5, then swap with the greatest child. Now we'll see again, 5 has two children, 29 and 15. So the greater child is 29. So it will compare if 29 is greater than 5 or not. So 29 is greater than 5, so it will swap. Okay, so now we can say 29 is greater than of its two children, 5 and 15. So the final result is a heap here. Sometimes it is not necessary to swap all the way down through the heap. If 5 would have been greater than or equal to both of its children, we would stop there. So we don't have to swap it every time if it's not greater than. Okay, heapify. So the process of swapping downwards to form a new heap is called heapifying. When we heapify, it is important that the rest of the structure is a heap, except for the root node that we are starting off with. Otherwise, a new heap won't be formed. A loop is used for heapifying. The number of times through the loop is always log n or less, which gives the big O log n complexity. Okay, so now we'll look at an example for InQ. Now value to InQ, we want to insert 37. So if you create a new node in the last position, say let's say we want to insert 37, and So we need to create a new node in the last position. Here, like that, we created another node. Now we'll place the value to enqueue in the last node, 37. We are adding it in the last node, like that. Now if 37 is larger than its parent, we will swap. So now we are doing backwards. Now when we are doing dequeue, we just went through the root. We started from the root and went down, and now we added enqueue. We did the enqueue, and we'll now check from downwards, and then we'll see if the parent is larger than the if the node is if the child is larger than its parent or not. So if it's larger, then it will swap. Now let's check. 37 is greater than 24, so it will swap. Then we'll again check if 28 is if 37 is greater than 28. So as you can see, 37 is greater than 28, so it will swap. If you notice that 37 is guaranteed to be greater than or equal to its children, because we compared it first and then we swapped. It was greater than the value swapped with 28, or we wouldn't have swapped. And 28 was greater than the other node 2, or it wouldn't have been a heap. So 37 must be greater than the other node 2 as well. So now we'll see if 37 is larger than its parent. 37 is not larger than 39 at this point, so it will not swap, and the result is a heap. Now enqueue uses a loop, and it is a big O log n operation, swapping in reverse. Okay, implementing a heap. Although it is helpful to think of a heap as a linked structure when visualizing the enqueue and dequeue operations, it is often implemented with an array. Now let's number the nodes of a heap, starting with 0, going top to bottom and left to right. Here, like that. Okay, now if you look at this tree, now in this tree we have 0 to 16 numbers. So 0, 1, 2, we did the numbering for the whole tree. So the root is 0, and then first child is 1, second child is 2, and then 3, 4, 5, 6, 7, so until 16 we numbered the we numbered as an array index. We are calling it as an array index. So if you look at here, left child equal to 2 multiplying by parent plus 1. So if you look at here, 2 into parent plus 1. So if you look at this 14, so the index is 7 here. So 7 is the parent of 11 and 9 here. Now if you multiply 7 by 2, 7 into 2 means 14, and then if you add 1, 14 plus 1 means 15, which is the left child value here. If you look at here, so this equation is by using this equation you are getting the value, the index value of the left child. So as we added numbers, index numbers from 0 to 16, you can calculate the number of your left child using this equation. So like that, similarly, if you look at here again, parent is 24 and the index is 5 here. So if you multiply 5 by 2, which is 10, and then add 1, which is 11, and which is the index of left child is 5. So that is how you can use this equation to find your index of your left child. For you, so again, if you look at this one, 16, the index is 3 into 2 is 6, and then add 1, 7 is the left child index address. Similarly, you can also do this thing for right child. Now here, if you look at here, 2 into parent plus 2, if you do that equation, you will get the index for right child. If you look at this one, 2 is the index value of 28, and then if you multiply 2 into 2, which is 4, and then add 2, which is 6 is the index value of your right child. Similarly, if you look at here, 1 into 2 means 2, and then add 2, which is 4 is the index of right child of 39. Again, if you look at 7 into 2 means 14, and then add 2, which is 16. That's the right child value, index value. So this is how you can get the address of your child, and you can do this using your parent address. You can find the children address. Now if you want to find out your parent address using child address, so you will then subtract 1 from child and then divide it by 2. Then you will get the parent address. So if you look at this one, the child value is 13 here. If you look at this one, child 13 minus 1, 13 minus 1 is 12, and 12 if you divide by 2, it is 6. So 6 is the parent index value. So this is how you can also find the parent value from child. Similarly, if you see 5 is the child minus 1, so 5 minus 1, and then divided by 2, which is 2. And then again for 4 minus 1 is 3, and then 4 minus 1 is 3, and then if you divide 3 by 2, you will just get 1. That will be a remainder, not the divider actually. So you will get the remainder 1. So that's all for today's lecture. We'll continue for part 2 on next lecture. Let me know if you have any question or concern about this topic and the whole lecture. Thank you.